So welcome everyone to iTelescope. My name is Christian Sass. I'm the astronomer in charge, and today is all about gas giants. I'm very pleased to introduce to you Sabina Sagynbayeva, and she's an astrophysics graduate student from Stony Brook University. So this is very interesting, things that are much larger than Jupiter or so. So Sabina, welcome, come in. Hope this is going to work now. Hello, how are you?
Hey,
Very
thanks
nice
for
to see
having
you.
me.
Very nice to see you. We're really looking forward to it. So without further ado, I'm going to hand the stage to you and we'll all listen. Thank you. And we'll put the questions and answers at the end. And if you wish, we can do that anytime in between. It's completely up to you. Okay.
Great, yeah.
Okay. And let me know when your poll is. Okay. And then I'll launch it. Thank you. I'll be quiet now.
Thank you so much, Christian. So let me give me a second to make my screen larger. So can you all see my screen? Well,
I can. I'm sure the others can. I'm just going to see if they have any comments, but I'm sure they can. Just go ahead.
okay, great. So thanks again for having me. I'm really excited to talk about things that I think about on a daily basis. So I think a lot about planet formation, and especially the formation of giant planets or gas giants. And today I will talk about that, about the series that we have. And I will also, as a bonus, talk about how we can form satellites, so the moons of those gas giants. As Christian said, my name is Sabina. I'm a PhD student at Stony Brook University. I'm originally from Kazakhstan, so you might notice some Russian accent. And you can also scan this QR code, which will go to my website, where you can read more about my research. But in order to start talking about how we form gas giants, I think we should take a look at the planetary architecture of the solar system. So next to the sun, this picture is not to scale, but closer to the sun, we have these terrestrial planets, Mercury, Venus, Earth, Mars. So the terrestrial planets are the planets that mostly have this solid core and some thin atmosphere around it. So the atmosphere is what we breathe in and breathe out, the air, and the solids are like this, mostly these rocky materials. Atmosphere is like mostly gas, and usually when we talk about gas in the universe, we usually refer to helium and hydrogen. Then we have two gas giants, Jupiter and Saturn, and we have these ice giants, Uranus and Neptune. And they're mostly, we call them ice giants because they're mostly these balls of ice with a little bit of atmosphere. But Jupiter and Saturn, these are just like balls of a lot of gas. And they have like truly so much gas that Jupiter is considered the most massive planet in the solar system, even though it doesn't have as much of a rocky material relatively to its gaseous material. But there's so much gas and so compressed in this like one little region, kind of little region. So let's look closely to Jupiter. Jupiter is really interesting, and this is the gas giant in the solar system. And the things to know about Jupiter is, as I said, that it is very massive, the most massive planet in the solar system. But we also think that it's the planet that formed first. So, and I will talk more about that later. As I said, it is mostly gas. In fact, we don't know the composition really of its core. So there's a lot of research going on to understand the composition of the core, the mass of the core. We don't even know that. We haven't reached consensus on that. But we kind of think that Jupiter, underneath that, all of that gas should have some core. What's also cool about Jupiter is that because it's the first planet that formed and it's so giant, and you might have learned from your physics classes that the more giant means it has really high gravity. So and it has this ability to attract objects or to excite them. And what we think is that because Jupiter is so giant, and it might have structured our solar system. So it excited all of these smaller objects, and now we see the small objects where they are right now, because Jupiter told them kind of with its gravity where to be. So whenever this small object was like passing through Jupiter, it had some gravitational effect from Jupiter and from the sun as well. We also think that Jupiter formed quite quickly, and I will talk about that later as well. And another cool thing about Jupiter is that it has a lot of moons, while Earth has only the moon. Jupiter has like around 80 or 90 of them, but this is a picture of 4 kind of most important moons, like the moons that researchers usually focus on because they have some potential for life. And we also call them Galilean moons, and they're also one of the most massive moons in the solar system. But other stars in the universe also have planets, and we were able to detect them. So I'm curious if you know how many planets researchers have detected around other stars. And we call those planets exoplanets or extrasolar planets.
Okay, so we launched a poll, so just jump in and guess.
Yes, so everything that you see on the sky, you see like a lot of stars. Well, if you're not in New York City like I am. But yeah, the sky has stars, and all of the stars have or should have planets around them, just like the sun.
Okay, we'll give a few more seconds and then we'll see, just about 20 seconds and then we'll see. So please take take the opportunity.
Oh, I'm sorry. I just showed the answer.
That was funny. Oh, that's sorry, I really have to laugh. Okay, we'll end the poll, but you know, in all fairness, these were answered before you were just showing something on your
Yeah, no, I believe that.
Okay.
Okay, great. Yeah, so the majority of you was right. Well, I wish the answer D was correct, honestly, but we only have detected around 5,000 planets. So so as I said, we have more than 5,000 detected exoplanets, and the researchers have been really clever about detecting them. This is the plot that I plotted like a week ago that shows planetary radius in terms of Jupiter radius. So this is, for example, 1 Jupiter radius, and this is smaller, everything that's like smaller in radius than Jupiter. And this shows planet mass in terms of Jupiter masses. So this 10 to the 0 is 1, so this is 1 Jupiter mass. And this is the whole population of detected exoplanets that we have right now. And here I also I'm also showing the Earth. It's here in this radius versus mass diagram. Here's Neptune, here's Saturn, and here's Jupiter. So Jupiter, 1 Jupiter radius and 1 Jupiter mass. And I also color-coded these dots. And these red dots show the population of what we call hot Jupiters. Hot Jupiters are the planets that are kind of the same radius and mass as Jupiter, but they're also closer to their stars. So they're so much closer to their stars than Jupiter is to the sun. And in fact, they're closer to the stars than Mercury is to the sun, which is really interesting. And in order to understand this whole population of hot Jupiters and understand like what's going on with Jupiter itself, we need to understand the evolution and formation of those planets. That's why I have my job. That's why I study gas giants and their formation, because I want to understand how all of this a lot of dots were formed. And this is a textbook that actually goes into detail of what we know about the astrophysics of quantum information. So it is very theoretical, and to be honest, I'm very biased because this textbook was written by my PhD advisor. But my PhD advisor, being an expert in the field and also a very clever person, on the cover of his textbook, he put this object. And we call this object HL tau. So, and this is actually a real object, and it is an observed image. It was observed by ALMA collaboration. ALMA is Atacama Large Millimeter Array. And I'm curious if you know what this shows. What is this object?
I would love to ask, has anybody else than you read this book who's in the audience? That's an interesting question.
It is really physics heavy.
I believe it would be, yes. Okay, wait a few more seconds.
But yeah, you can just Google what HL tau is, but that's not fun. Okay, great.
Smart people.
No, yeah, I call it the planetary donuts myself. So 4 of you were kind of right. But yeah, most of you were right. We call this thing a protoplanetary disk. And actually, I was trying to be kind of vicious here because we have objects that are called circumplanetary disks, and I will go back to them later. But these particular objects are called protoplanetary disks. And one of the takeaway messages from my talk that you should get is that planets form in disks. So what are the protoplanetary disks, right? Protoplanetary disks are a huge pile of gas around a newly formed star, around a young star. So we have a young star somewhere here in the center, and everything else here is gas. So as I said, mostly hydrogen and helium. There are also a little bit solid materials, some silicates, but in my research, I don't care. So it's mostly gas because it's actually, yeah, it's like 90% gas. And all of this gas is orbiting around this star in the middle. And because these disks are comprise most of gas, what we do in theoretical astrophysics is we try to make perform some hydrodynamical simulations in order to understand the physics of planet formation. Because the disks, these protoplanetary disks, this gas again, is a birth environment for planets. So if we have some star somewhere here in the middle, planets form somewhere here or here. And because it's mostly gas, we try to understand so because it's gas, it follows the laws of hydrodynamics. So in order to understand the planet formation, we need to understand this gas-planet interaction. So it's mostly governed by hydrodynamical equations. That's why what we do is we try to perform some computer hydrodynamical simulations in order to understand the physics itself. And also, it's really hard to observe forming planets because they form in like millions of years and we don't live that long. That's why we have to run hydrodynamical simulations in order to see the whole evolution and the formation of the planet. But what's also cool is that this is, as I said, real image from ALMA. And so are these. These are all the images of protoplanetary disks. We have observed them, so we're pretty sure that protoplanetary disks exist, and we're pretty sure that planets form in protoplanetary disks. And as I said earlier, Jupiter is the first planet that formed in the solar system. And here's why. That's exactly linked to the fact that planets form in protoplanetary disks. This is my favorite theory that's called core accretion. There are a lot of people that might argue with me, but I love this theory because it's so kind of easy to understand. What I'm showing here is the plot. On the x-axis, we have time in millions of years. And on the y-axis, we have mass in terms of Earth masses. So here it is 20 Earth masses, 40 Earth masses, etc. Here also, this is actually the plot from a hydrodynamical simulation from 1996. So people were clever about that as well, even back then. What we have here is this solid line shows the evolution over time of a planetary core. This dotted line shows the evolution over time of gas, so over planetary atmosphere, or we also in planet formation field, we call it planetary envelope. And core plus gas equals planet. So this dashed line shows the evolution of the planetary mass, like altogether. So as you can see, the core does not increase too much over time, but gas that's like around the planet, around this core, at some point starts increasing rapidly. And this is the idea behind the core accretion is that because at some point when you reach some planetary core mass, it becomes massive enough to attract gas. As I said, again, gravity, it becomes massive enough to attract gas. And the more gas it attracts, the more massive it becomes as well. So it attracts even more gas and even faster. That's why there you can see some bombardment of gas onto the planetary core. That's why here the mass increases so rapidly and so quickly. Yeah, but because this theory was introduced in 1996, this particular plot is quite outdated, but there are still people trying to understand core accretion theory. And this is another plot that shows the same core accretion. So it kind of, even like in 2020, we could see the evidence from hydrodynamical simulations for core accretion. But here you also have to add some other physical phenomena because it's really complicated physics all around. You have gas orbiting a star, and then you put some planet on and gas accretes onto the planet, and it's like a lot of physics going on. But as I said, protoplanetary disks have some like solid material as well, some silicates. And here the researchers also show the core accretion, but they also added some accretion of the solid material, not only the gas. And we call this accretion planetesimals. And here researchers included the gap opening. So here I'm kind of smoothly going into the next topic, which is the opening of the gap by giant planets. I know these are a lot of plots, but don't overthink this. I will explain to you. So what you see here is the surface density of the protoplanetary disk, and here's the distance from the planet. So here, where the planet is located in the simulation. As you can see, surface density drops here, which means that planets open gaps, like literally gaps in protoplanetary disks. So what you have is gas, planet with a gap with no gas, and then gas again. Here I drew this cartoon that shows it. Here we have gas. This is all protoplanetary disk. You have a star, you have a gas here, and then you put a giant planet into the gas, and then it opens this gap where you have almost no gas. And then you have gas again. So this is really interesting, and this is the results of many hydrodynamical simulations. What also happens is because again, as I said, it is very complicated physical process, you also can see this kind of spiral structure, spiral arms. This is the result from one of the many hydrodynamical simulations where they show the gap opening. So again, hydrodynamical simulations just follow the laws of hydrodynamics. So this is what happens following the laws of hydrodynamics. If you just have a lot of gas, you put a planet in there, it's going to open gaps, just like this is what the hydrodynamics tells us. So you have a planet in here, and this is the gap that it opens, and here as well. And these are like actual simulations. This is your simulation from my own work. We have a planet here. We have some spiral arms, some spiral structure here. And you can see this, we have this black material, which indicates no material. Yeah, but also what you can see is that it is actually a Jupiter-sized planet here in my simulation. You can see there's some going on, something here, some structure here. And this structure here, because it's kind of like that seamlessly connects to these spiral arms, is called circumplanetary disk. And I know that astronomers are very good at naming things. I know that. So what we actually have is we have protoplanetary disks, and we have circumplanetary disks within the protoplanetary disks. So, and the cool thing is that we could observe some disks around brown dwarfs as well. So these are the actual observations of kind of circumplanetary disks around brown dwarfs. So brown dwarfs have the objects that are like planets orbit around massive stars. And here we can see the observations of some disky structure forming around them. But we also have actual observations of circumplanetary disks as well. Here you can see the observation of a system that's called PDS-70. This is the protoplanetary disk that I think it's from ALMA that ALMA observed. And this disk has two protoplanets, or protoplanets as the forming planets. So PDS-70b and PDS-70c. And PDS-70c has some circumplanetary structure around it. So this was, I think, the first observation of circumplanetary disk, and they're so hard to observe. And so this is quite cool. And let's understand a little bit better what circumplanetary disks are. So here again, this is the cartoon that I made if you cut the protoplanetary disk vertically. So you have a star and you have this gas. This is all of this orange is gas, and this is actual protoplanetary disk. And I know again that astronomers are great at naming things, and I know that we call them disks, but they're actually not these razor thin structures. They have some thickness, and they also don't look like cylinders, because this thickness kind of like gets bigger as you go in distance. So this is like how protoplanetary disks look like. You have a star and you have like this like gas around the star, and it all also rotating. And you have a planet here. So, and around this planet, we have this kind of structure that we call circumplanetary disk. So, as I said, it is literally disk within a disk. And the planetary formation research becomes more exciting the more simulations we make. This is actual simulation that shows the structure. This is what I said. This is another cut of a protoplanetary disk. This is a planet inside of a protoplanetary disk, and the structure actually shows the circumplanetary disk. And what people try to understand with these simulations, when we try to understand the physics of the planet formation, is we try to understand how the material, how the gas flows from the protoplanetary disk onto the circumplanetary disk, because it actually indicates how material goes onto the planet itself. And so we try to understand its fluid dynamics around a planet. And what we actually have seen from the simulations that this flow is not really easy to understand. This is kind of, we have this kind of like meridional structure kind of flow. So it's not only horizontal, gas doesn't go like onto the planet horizontally, especially as I said before, because we have gap. So like gas cannot easily escape the gap and go onto the planet. It has to go vertically as well. And what's cool about that is that we have observed this kind of similar structure, this kind of similar circulation of the gas around the Neptune mass planet. I'm not gonna talk in detail about this plot, but this is the plot that actually shows the observational evidence of this meridional gas flow around the Neptune-sized planet. And if we go back to the architecture of the solar system, what we also can notice is that these giant planets have a lot of satellites, they have a lot of moons. And extrapolating my logic, if planets form in the disks around the stars, then moons probably form in the disks around planets. So, and this is actually how has proven to be an efficient way to form satellites. So circumplanetary disks are very efficient to form moons around giant planets. And this is another cartoon that I made to make it even clearer, more clear what I mean by this whole structure, that like the whole physics that we're trying to understand is that we have the star, we have protoplanetary disk around the star. We have this planet that opens a gap that has the spiral structures, and also it creates this circumplanetary disk. And inside those disks, we create moons. And this is another simulation from Joy Julagi that actually shows the formation of those moons inside the circumplanetary disks. So in summary, the take-home message from me should be that, first of all, planets form in disks. We call them protoplanetary disks. Another take-home message is that satellites form in disks, and we call them circumplanetary disks. I know it is very confusing, but most importantly is that the physics is so complicated, but there's so much to learn that we're very excited about it. Thank you.